Pronto? Yes, I hope you can hear me well. Thank you very much for having me today and for the very accurate introduction. Today I'm going to describe the latest updates on measurements of the expansion history of the universe with the latest data release of the LIGO Virgo KAGRA collaboration, and in particular the latest catalog of transient sources called GWTC-4.0. Do you want to hear it? Hello? Better? Good? Okay. So I will actually start by giving a quick update of the catalog itself, which contains a couple very interesting sources I will not have time to discuss today, before moving to what is actually of interest for cosmology and for expansion history measurements, which is the possibility of measuring distances directly from these transient sources. Then I will describe in more detail, and I want to spend some time on this because it's one of the major advances that we made in this paper, describing the methods and the statistical formalism that is behind our measurement before discussing results. I will also introduce some tests of deviations from GR at cosmological scales that we introduced in the paper, and I'll reserve some time for the discussion at the end. Let me start by describing the catalog. I want to advertise the fact that together with the data release, there's a huge amount of work that has been devoted to writing papers that introduce the methods and broad concepts behind the detection and use of gravitational waves in different domains that I really suggest you to read in case you are interested, in particular the introduction paper here, which is a broad overview, and then the rest goes more and more into the details of detection and data analysis. And in case you are even more interested, our data and catalogs are available open source, in particular the parameter estimation, and you find them at the links described. Let's look at those sources and to the detector operation a bit closer. What I'm going to discuss today, so what we call the GWTC 4.0 catalog, is based on everything the detectors observed since 2015 up to January 6th, 2024. Here you have a timeline of the operating times of the detectors given by the colored vertical bands. And the novelty with respect to previous data releases, the results I'm discussing will be based on, belong to this chunk of observations, which is called O4A. The colored dots here and the bars here and the numbers denote the detector reach. So it's a metric to give a sense of how far the detector sees, and it's the maximum distance we can observe a binary neutron star system at. Also, you'll notice these are the different detectors making our network. You'll notice the Virgo detector was not, unfortunately, operational during this first part of the fourth observing run. So the new data I'm discuss will be two detector data. This is a timeline of the cumulative detection rates. And again, the yellow part is the novelty. The change in slope gives you a sense of the improved sensitivity of the LIGO Virgo detectors. And this observing time delivered 128 new candidates. I'm talking about transient sources here, which make a total of 218 if summed to the previous ones. Just to give you a sense of the sensitivity, this is the sensitivity curve taken at the representative time of the O4A run, and this is a 10 to the minus 23 in the detector strength, so in the differential arm length. I know you'll probably know these numbers, but I think they are quite impressive every time I look at them. This is the detector duty cycle, so 53% of the time we had coincident data between the Hanford and Livingston detectors. Let's look at these sources a bit closer. This plane shows detections in primary mass, so the mass of the heavier object, and secondary mass, the mass of the lighter. Most of our candidates are made of binary black hole systems that live in this square up here from around 5 to around 150 solar masses. And there is a couple exceptional candidates detected during the run. In particular, I want to highlight the heaviest black hole ever detected with a total mass of more than 200 solar masses up here, and there are special event papers associated. I want to highlight the loudest binary black hole detected in the run with a signal-to-noise ratio of 42, which is really exceptional. It was a single detector event here, and it lies around here. If we instead look at the lower part, so below 2 solar masses, we have systems made of neutron stars, and here systems made of a neutron star and a black hole. In particular, we detected one event made of a black hole and what could be either the most massive neutron star ever detected or the lightest black hole. The debate is open. Finally, as you know, unfortunately, we did not detect any multi-messenger event during the run. This was a quick look at the ensemble of our sources. Something else that I wanted to point out is notice these black holes tend to cluster a bit around 35, 40 solar masses and around 10. This will come back later, so remember this information for the following because it's important for what I'm going to discuss. Rather than just masses, I want now to turn into discussing in more detail the way we measure distances from these sources, which is the key ingredient for cosmology. And let me review the standard argument behind what we do. Consider, so these sources, I think you cannot see the titles of the slides, and I'm sorry for that. Yeah, but I don't see the error, the bar, so. Now, because I don't see the arrow on my, sorry. So I do OK, then I was here, then I hide, and then I do play. Yes. All I wanted to say is you maybe have heard that we call our sources, so compact binary signals, self-calibrated distance tracers, or maybe you heard that gravitational waves are distance tracers calibrated by general relativity. And I wanted to clarify a bit what we mean by this. So consider a binary at cosmological distances. I will call its parameters the source frame parameters. So it has some masses and it merges at some redshift far in the universe. Here we can compute accurately the emission of gravitational waves according to general relativity. We know there are two polarizations that we call the plus and cross. And we can compute the phase and amplitude evolution of the signal. In particular, the phase evolution at leading order is determined primarily by a special combination of the masses that we call the chirp mass, because the signal increases in frequency and amplitude, giving it the characteristic chirp shape. This same chirp mass determines the amplitude that also depends on the merger frequency and inversely on the distance. Then this signal has to propagate through an expanding universe and is detected here. I will refer to this as the detector frame. And it carries the imprint of the expansion in at least two ways. So first, frequencies and times undergo redshift, and then the propagation equation for the waves has a friction term, which is essentially given by the Hubble expansion. If you combine these elements and look at how the waveform changes, first, you will realize that one can completely reabsorb the redshift in a redefinition of the mass. So our detectors never measure the intrinsic mass of the sources, but only this particular combination of intrinsic mass and redshift. And this is true for all mass scales in the problem, not just the chirp mass. So it is impossible to determine redshift directly, but the interesting thing is that the amplitude of the strain scales inversely with what is the luminosity distance to the source. So here we get really the same luminosity distance that you will get by comparing the intrinsic and observed flux of an electromagnetic source coming from the same place, right? And this is directly got from the detector strain. So by measuring the phase, we fix the detector frame mass, we know the merger frequency, and then we determine directly the distance. And there is, of course, cosmology here, because this is the expression in a flat lambda CDM universe, and associating redshift information, you can extract, for example, the Hubble constant. Now, the point here, which gives the name to these sources, is that in this reasoning, I didn't rely on any astrophysical knowledge of the source. So this is only general relativity that gives this property. And this is why we use these definitions, and we call these sources standard sirens in analogy to standard candles. Now, this is a quick summary that tries to grasp the essential physics behind, but in practice it is not so easy to obtain clean distance measurements, right? So this seemed very quick and straightforward. The reality is much more complex, and I want to spend 2 minutes to give you a closer sense to what we have to do and why the distance is still hard to measure and to extract. First, the signal we see is not, we don't measure the polarizations directly. We measure a combination of the two projected on the detector plane through these functions that we call the pattern functions of the detector and depend on the geometry and location of the machines. So if we look at the sensitivity over the sky, it's not perfectly uniform, actually. This is the so-called antenna pattern that measures the sky sensitivity of the LIGO Virgo network. We have, for example, spots where the accuracy, so the sensitivity is not zero, but it's lower. So depending on where you are, you might be sensitive in a different way to the signal. The most important thing is that we need, as you probably know, we do not point gravitational wave detectors. They're more like microphones. So we need at least 3 of them to triangulate the source by comparing the arrival times. If you had only 2 detectors, this is the LIGO Virgo KAGRA network, you could localize the source to a circle in the sky, and you need a third one to actually pinpoint the location. And here I isolated, this is the sky map of a public alert of the collaboration with the 2 detector event. And so you recognize the ring pattern. And this is a 3 detector event during O4B, where you see by eye the argument I was making. This, of course, makes distance measurements with 2 detectors much more inaccurate. Next, we have an intrinsic characteristic of the waveform. So I went a bit fast on the 2 polarizations, but the main difference between them is how they depend on the geometry of the system, and in particular on this angle between the orbital angular momentum and the direction of observation that we call iota or inclination. So actually one could mistake a different inclination for a different closer or larger distance. So more technical terms, there is a strong correlation between the two. Here you see the distance inclination plane for the binary neutron stars GW170817, and this correlation is more important for low inclination sources, so where these two are almost aligned, and it translates into a high tail of uncertainty in the distance to the source. And then, of course, we have in general detector noise, which is hard to beat and makes these measurements difficult. So all this to say the final product of our distance measurements is a complicated thing, and it's the result in general of a more than 10, usually 15-dimensional Bayesian parameter estimation with multimodalities and correlations. As a result, so this is a sketch of where we stand. On the left, you see the relative distance uncertainty of the sources in the catalog as a function of redshift, which I take to be the distance converted with the Planck cosmology. So you see typically they scale, so the further the source, the largest the uncertainty, and the bulk is between 40 and 70% relative uncertainty, which is a lot. There are a few notable exceptions I wanted to highlight. So this is the best event ever measured during O3. It was a very close by black hole with a very nice distance determination. Here you see the binary neutron star 170817, and you see it's much closer, but it lies higher in the relative error, and you might wonder why, and the reason is precisely this strong correlation with the inclination, because this was a low inclination event. You can also notice our friend here with the scenario of 42, the loudest black hole I was mentioning before, and this, despite being fairly close, was a single detector event. So the distance determination is much more complicated. On the right, you see instead the sky localization of the sources, and the gray events in particular are those detected during O4A. So you see we don't have not anything below roughly 100 square degrees as a consequence of only 2 detectors being operating, which wasn't the case in previous runs. So this is a quick summary of where we stand with measuring distances and sky position, so tracing our sources in the sky. Now I'll go to the next part where I will describe more in detail how do we associate a redshift to these sources and then try to extract measurements of the expansion history with them. In general, we call any method related to associating redshift to distance a siren method, and there are different names attached to them. I want to convince you today that actually all these are part of the same underlying statistical framework, which is determined by one idea, which is in absence of a direct redshift information, what we need to do is to analyze and combine the ensemble of our sources and check their population properties, comparing them to some knowledge expectation for their shape, which, as we will see, give information on the redshift. And now I'll go a bit more in detail into the statistics of the problem. So what we want to do is to forward model, to have a generative model for the way the catalog we observe is generated. And we call this method hierarchical Bayesian inference. Hierarchical because it involves several levels, one after the other, as shown in the Bayesian graph here that now I will discuss. At the higher level, we have the population. So we assume black holes merging compact binaries in the universe are a realization from some underlying probability distribution that tells us how likely it is, say, a black hole merges at a given mass or at a certain redshift. This distribution will depend on astrophysics, so will parametrically depend on parameters that say, for example, the slope of the mass spectrum that tells us how, if it's more likely that a black hole has 10 solar masses or 50. At the second level, we have the single source parameters, so every set of parameters in the source frame that I call theta here, the masses and redshift, are a draw from this probability distribution if you want, and in the detector frame, they become detector frame parameters through a conversion that depends on cosmology, so the typical redshift to distance relation, for example. At the third level, we have everything related to detection. Meaning for every parameter here, we have a realization of the data, so a realization of the noise in the detector at the moment the signal arrives, and this is described by a likelihood function that gives the probability of having a given data realization knowing the true source parameter, which is essentially a model of the noise of our detectors. At the last part is really the detection, so the probability of detecting one event given the stretch of data. And this term determines essentially which events make it into the final catalog. So they could be assigned to as or labeled as confident detections based on some ranking statistics. For example, if the signal to noise ratio is large enough. And our job here is really to reverse engineer this process, which is again something that goes in different steps. So at the first level, you know, the LIGO Virgo detectors are quiet most of the time, meaning noise dominated. And just a few times in a year, there is a signal that lasts less than a second that gives trigger in a detector and which is identified as a confident astrophysical candidate at this level. Then for that data stretch, we analyze the data in more detail. That's the parameter estimation problem I was talking about before, and extract the source properties, distances and masses. And then our job, which is what I will describe today, is to climb the third step back. So combine these sources detected and determine the properties of the populations those sources were drawn from. I can translate all these in a likelihood function for the problem. In particular, we are interested in reconstructing the probability distribution for the parameters lambda, both cosmology and whatever describes the population. So what we do is this. We combine measurements, which is this product, considering the events statistically independent. And then for each mass or distance measurement here, we reweight our measurement by the expectation given the astrophysical model. Crucially, to do this, so to compare the measurement in detector frame to what we expect, we need to convert masses and redshift and distances measured in detector frame to source frame masses and redshifts, which depend on cosmology. So the idea is that the reconstructed shape of the population will match the expectation only for the correct cosmology. And I will show specific examples of this. So first, the crucial ingredient is to model this, and the second relates to the process in the orange box. So we need to correct our likelihood, our measurement for what we call the selection bias of the detector, meaning the fact that not all sources are equally likely to be observed. Heavier black holes give louder signals, nearby sources give louder signals, so it's more likely that we pick them and we include them in our catalog, and therefore we need to correct our measurements for the fraction of observed events, which is this quantity that I call psi here. Crucially, to compute this function, we need to know the detection probability. So for each given source, we need to be able to tell how likely it is that this is detected, and which is a non-trivial job. I will describe in more detail how we do this in a few minutes. This part probably sounded a bit abstract, and I am aware of this, but now I want to give more specific details of how all this contains physical information, actually, about cosmology in particular. So let's look at some specific cases which are what we do concretely to obtain our measurements. The first thing we need is a model of the mass distribution. So here we measure masses and distances, right? So this is encoded in some model of the mass distribution. Now, suppose the mass spectrum of black holes is not flat, meaning black holes form in the universe preferentially around some mass in source frame, okay? We call this a feature, so say a peak in the probability of forming a black hole. This feature is then observed in detector frame. So depending on the distance where you are, you observe its position shifted by a factor 1 plus redshift, which is what I show here. Now, if we try to reconstruct the position of the feature from the detector frame measurement, we have to convert back the masses to source frame. And if we shift the value of H naught, the position of this peak or this feature will be shifted accordingly. So at some point, it will not match anymore our expectations. And these can inform the measurement of H naught. We call these effect, these sources, spectral sirens for this reason. Now, the important point is that these features are present in the observed mass spectrum of black holes. So this figure here shows you is taken from the collaboration paper that looks into population properties from GWTC-4 data. And it shows the probability that a black hole has a certain primary mass, M1. So you see we detect a peak around 10 solar masses and then a power law decrease here with a bump around 35. Now, if I varied the value of H naught when reconstructing this peak, I will shift its position to the left or to the right according to which H naught I choose. So eventually this becomes informative on cosmology. Next to masses, we have redshift. So the second thing we can do is to associate a probability distribution to the fact that a black hole merges at a certain redshift. And here we apply an idea which was put forward by Schutz in the 80s. We call these dark sirens. And the idea is conceptually pretty clear. So look at this. This banana shape is the localization area in the sky of the first gravitational wave event ever detected. And the crosses here are galaxies in the localization region. So I take a galaxy catalog and just look at the galaxies that fall into that banana, okay? What I can do is to consider each of them as a potential host of the event and compute H naught by associating that redshift to my distance. But I don't know what the correct galaxy is. So what we do is to marginalize over the choice of the galaxy. We can do this associating also some prior probability that a galaxy is more likely than another to host an event based on intrinsic properties like mass or luminosities. A crucial point is if the catalog is not complete, we need also to account the fact that we might be losing some objects due to, say, for example, the flux limit of the telescope or the limited footprint in the sky. And if we look at a toy example I made, we can construct for each direction in the sky a redshift prior which will be given by all the galaxies in the region, which is this black curve, which is then convoluted with the distance measurement from gravitational wave. Now, these will be placed at different redshifts. So each of these distributions is a distance measurement converted to redshift with different H naughts. And you see this will align with different peaks depending of the value I choose. In this case, I chose 70 as the true one, and the true redshift is here. So these two align only for the correct H naught. Of course, if I have many galaxies, I could, for example, think that the correct H naught is this and the host galaxy is here, right? So I will have spurious determinations of the Hubble constant. Now, the point is that I can combine many events, and if each of them might give spurious peaks, when I stack them together, the true value will be singled out by statistics. And this is nicely shown. This is a real simulation from 2019, so with the realistic data, and you see it recovers nicely the injected value once hundreds, tens or hundreds of events are combined. Now, in all these, you might be wondering, where is the most simple, trivial case, right? The one where I know where the source is. This is called the bright siren, and you're probably aware that we detect the LIGO Virgo detectors in coincidence with the Fermi GRB detected one in 2017. So in this case, the Fermi GRB localized the source around here, and the gravitational wave sky map was here. So in this case, you can pinpoint the host galaxy because an electromagnetic emission, in this case the GRB, is associated to the merger. In this case, well, it's just that this galaxy catalog prior collapses basically to a delta function. So you single out the galaxy, right? and measure H naught directly. So this was the case in 1917. And I will use the information from this source. But what the message I wanted to send is that all these methods are actually different flavors of one statistical model and one idea, which is describe population properties. And from these, either astrophysical information or redshift determinations from other experiments build prior knowledge on where you think your sources are in redshift. Before moving to the results, I have a few things to highlight here at the methodological level. So there are two key ingredients here. One is this and one is the other. So first is the population model. Notice that if this population model is a valuable source of redshift information, it's also difficult to model. And I will describe what we do. But the point is, whatever you do, you need it in order to consistently account for the detector bias, because this population model enters here, and this term needs to be computed very accurately, whatever the source of information is, if you have redshift, mass, or anything else. Therefore, what we need to do is to estimate anything related to population properties and cosmology together, because I talked about features in the mass distributions, etc. But of course, we don't know where the location is, right? Because we don't know the population. That's actually the very reason why we do these studies is to determine population properties of black holes alongside cosmology. Therefore, the parameter estimation problem becomes a high dimensional one in usually more than 20 dimensions with this is a high dimensional integral to compute at every step, and the details are not trivial. This possibility of estimating everything together is a major step forward we make here with respect to previous collaboration analysis where these things were somewhat done sequentially. And our analysis codes, there are two independent that we cross-test, are available open source. They are called GW Cosmo and Icaro GW. A final note is I was anticipating the crucial ingredient here besides population is reconstructing the detector bias. And this job is, believe me, really highly non-trivial. And we do it by injecting fake signal in the real noise of the detector, millions of them, and running the very same detection pipelines we apply to real data to record the ones that are detected over a large parameter space. This process is very expensive, both in terms of human and machine time. So if you ever want to understand or reproduce these results accurately, this is the data product I suggest you to master. And the related paper that describes how these sensitivity searches are performed. Finally, I began this presentation by telling you that only GR enters in the distance determination, right? So it is nicely GR calibrated and we do not need astrophysics. And now I'm here to tell you, whenever you combine more than one source and do any population study of this type, you accurately need to model the astrophysical population and know the detector bias. So whenever you see a paper mentioning dark sirens and galaxy catalog, please ask what they did for these two elements to understand if the results are solid. So astrophysics eventually come back heavily into play in all this. This said, let's move on and discuss results. This is really the content of the cosmology paper associated to GWTC-4. I will start with the Hubble constant. The results I will present are based on 141 events without a counterpart plus the bright siren 170817. Let's look at the models we use to describe the population. So the baseline model used to describe the binary black holes is this here. So we model the mass distribution as a power law with the possibility of having extra peaks, deviations, where black holes are slightly more likely to form on top of it. And we compare to a simpler model where only one peak is allowed, which was the best fit for the previous data releases. We'll see that it's not a good fit anymore and we need more structure. We have another novelty with respect to previous work, which is the use of a model that covers the entirety of the mass spectrum, meaning including also neutron stars and the neutron star black holes, so going below 5 solar masses. So this model includes a dip between, say, 3 and 5 solar masses and then an excess of neutron star. Of course, we estimate the position of these features. We measure from the data. We do not assume them to be fixed. And then on top of the galaxy catalogs, we associate a probability that a binary merges at some redshift following the star formation rate at low redshift, which is a power law with some slope that we also determine from data. As for the galaxies, we construct our redshift priors from an all-sky galaxy catalog called GLADE Plus, which is an assembly of previous surveys. It's essential to have the largest coverage possible because the gravitational wave detectors are all sky. This catalog is actually made by 22 million galaxies, but we only use those with an associated luminosity measured in the K-band, which narrows it down to only 1 million. This is unfortunate, but it's the subsample for which we understand the Schechter function in a very solid way. So we prefer robustness at the price of being very limited in completeness. This is the completeness basically above redshift 0.1. And this is an overview of the galaxy catalog with some gravitational wave on top. And you see the bad localization in O4A due to the absence of the Virgo detector. I wanted to give some more technical details on how we construct these redshift priors, but in the interest of time, I will go fast on this. Don't hesitate to ask me this during the questions if you want to see a bit more closer how we compute it. But in short, we pre-compute the galaxy distribution in each pixel in the sky here along the redshift by accounting for the incompleteness, assuming a Schechter function and that galaxies are uniformly distributed in comoving volume. And this is now the best result we have for the measurement of the Hubble constant. The best is given from the population model covering the full spectrum of black holes, and these results are marginalized over around 20 nuisance parameters. Here we fix the matter density to the Planck value, but it doesn't really have an impact if we vary it. We can discuss it later. The different curves here, the black is the full result. The bright siren 170817 is the yellow, while the dark sirens are these blue curves. So you see there is still a dominance of the single bright siren event we have, and dark sirens contribute to lower detail here. The baseline result is 76 plus 13 minus 9.5, which is not a huge improvement in the width of the error bars with respect to previous releases, but now I hope I explained that we do this in a much more robust statistical way. So the novelty here, I believe, is really the robustness of these error bars. Yes, well, this is partially the answer, right? So the dominant source of information here for dark sirens is, you see, dark sirens are the blue, so with the galaxy catalog, and without the galaxy catalog, spectral sirens are just the information based on mass scales. So the galaxy catalog improvement due to incompleteness is very modest. So the largest source of error of information here is the mass scales in the binary black hole spectrum, which are shown here. This is the full population model, and you see we find these peaks around 10 and a bump around 35 solar masses, which are given here by these parameters. This is mu high is the position of this peak and mu low is the position of the other. And you see they have a correlation, a large correlation with the Hubble constant. So this is the quick answer to your question, but we can dig more into this later during the discussion. So this also anticipated this slide. If mass model drive the constraints, we need to check how much it changes if we change the mass model. And in particular, here you see the one describing the full spectrum and the golden curve here, only limiting to binary black holes, show agreement in the location of the peak, even if the one restricting to black holes has a much a larger uncertainty due to few sources and fewer mass scales included in the model. The model with only one peak in the distribution is this, and it's really disfavored by the base factor here. So it's not a good description of the population, which turns also into a bad measurement of the Hubble constant. So that's really there only for comparison, and the solid results are the other two. Below, you find instead what happens if we vary the assumption about the probability that a galaxy hosts a merger, which we assume to be proportional to its luminosity in the K-band, comparing also to a random, so a flat probability here. So at this stage, as a consequence of the incompleteness of the catalog, this does not have a large impact, but we expect it could do in the future as more complete catalogs are available. Now,
so the results favor the local measurement?
I think it's too early. Maybe we can discuss this in detail, because yes, it's an interesting point. I think it's too early to take a position, but we'll see. There's room for discussion here. I wanted, before concluding and discussing briefly some perspectives, I also wanted to mention the possibility of providing some tests of general relativity at cosmological scales. And quickly, the idea we consider is this. So in the local wave zone where the waves are emitted, and in the detector frame, there are no modifications, but gravity could be modified during the propagation of the waves, so at cosmological scales. And the possibility, which is currently less constrained, is that the friction term they experience is different from just a pure Hubble friction. This is a typical phenomenon that emerges in theories with extra degrees of freedom, like scalar tensor theories, where a scalar is coupled to gravity. And the net effect is that the distance notion you measure from gravitational waves is not anymore the luminosity distance, so the same electromagnetic luminosity distance you will get from the flux. But we call it gravitational wave luminosity distance, and you can compute it directly as a function of this modification that I call alpha m here. The name alpha m really comes from Ordensky gravity for the experts in the room, because it's really the same function that modifies the canonical normalization of the graviton action. So therefore we call it a running Planck mass. So it's the possibility that the Planck mass evolves in time. We need to parameterize this function, and we assume it to be proportional to the onset of dark energy, because it's usually associated to these extra degrees of freedom used to explain the acceleration. Another possibility is parameterizing this ratio of the two distances directly, and we do it, a common choice is to use a parameter which is, if you want, the analog of W naught for the dark energy equation of state, so something that captures the overall deviation from lambda CDM. The effect is propagated during with redshift, so it cumulates. This is the distance ratio as a function of redshift, and it cumulates with the propagation, and the overall amplitude is this parameter here. So we can apply the same techniques we use for the Hubble constant, and we get here, here I show results in the subspace of these deviations together with the formation rate of compact objects, because these two have a large correlation, as you see. Why? Because the effect of modifications of gravity is accumulated during propagation, so you can mistake it, or it's degenerate, with a different shape of the binary formation history as a function of redshift. We find no deviations from GR, which is described by Cm equals 0 and psi naught equal 1. So these numbers are nice improvements over previous measurements. This Cm is also measured by large-scale structure experiments, in particular DESI, for example. Euclid will do as well. And our constraint is still worse by a factor between 25 and 60%, depending on assumption, by results by the results based on large-scale structure measurements, but obtained with a completely different method and systematics. So I think it's interesting to push for improvements in this direction. Excellent. So I have a summary of a robustness check if you want to ask me later, and now I just spend the final minute on discussing a bit, putting this a bit more into perspective. I think, as you saw, as the questions anticipated, so these results are really driven by mass scales, the presence of scales in the mass distribution of binary black holes. The catalog gave a modest improvement to the result, and this is a consequence of the poor completeness and limited localization capabilities, especially during O4A. Fortunately, we have better perspective for the rest of the O4 observing run, which is still ongoing. It will end in November this year, and after O4A, we detected another 150-ish candidates with the Virgo detector operating in coincidence with the other two. This is one of the best localized sources for which we release the public alert, and you see it's localized to about 5 degrees squared, 50%. So that's really a jump in sensitivity, and we look forward to analyze this data. Now, a key point is also having better catalogs, and we have a work underway to improve them as well, to combine with better localized sources. The catalogs we use need to pass a number of robustness tests before we include them in our results. We need to understand accurately their Schechter functions and look for a filter for impurity and other related things. So this explains why it takes time, but there is hard work ongoing. If you look at these forecasts, so this is a forecast for an optimistic O5 scenario. This is the error, but just look at the improvement in the error. But this is something based only on mass scales, and this is with the same gravitational wave samples what we obtain by adding a photometric galaxy catalog. And then the red is the jump between photometric redshift errors and spectroscopic ones. So we would really like to have spectroscopic samples as complete as possible to cover the localization regions of our sources and in order to deliver precision constraints. So that's I think, a really important point to push for. And the good news are, this is the error on H0 as a function of the completeness of the catalog. So under optimistic assumptions for the gravitational wave side. But the interesting point here is that we go towards the percent level precision. This is 2%, even with a 50% complete, if we can understand how to model the incomplete part. So that's also promising. And the final point I wanted to make is that the more redshift information we have, the more we can break these degeneracies with the mass scales, which also partly answers the previous question. So this is the correlation between H0 and the mass scale in absence of redshift information. And this is The same with the photometric catalog. So you see that this strong correlation is really broken here, which also makes this much less sensitive to the choice of the population model. This happens as a function of completeness. So now this is the same thing, but with a complete catalog in black, and the gray circles are what happens if we have increasingly less complete catalogs. This takes me to the end of the presentation. So I think this dark sirens method really made a huge progress in terms of robustness. That was the main message I wanted to send. We only have a single bright siren, so it's important to push for having these complementary sources under control and to be able to extract as much information we can by them in conjunction with galaxy catalogs. So as I said, the improvement in the size of the error bars, I think, is limited, but the robustness has made very significant steps. Gravitational wave sources by the same method can probe gravity at cosmological scales, which I think it's also valuable. And we didn't find any deviation from GR. We are aware of directions to improve as more data become available, so the error bars shrink. A crucial point is the population model. The models I described, for example, do not assume correlations between different parameters, so masses and redshifts are sort of decoupled, but we know as the precision increases, we will probably need to model this, and there is work ongoing. And a related point is to keep under control and work on addressing the systematics related to galaxy weighting and completeness as we work for more complete catalogs. This is all I wanted to say. So thank you for your attention.
Okay, we have a lot of time for questions and discussion. So you already have one here.
Thanks very much. I'm working a lot on Euclid, so I'm interested to know, first of all, can you tell me what's the average redshift distribution of your sources? Is a survey like SphereX, for instance, that's not interesting to you guys because the sources are too close?
So I think the most interesting sources for H0 are actually close-by sources. So close-by sources are surveys are definitely of interest, and I think SphereX could be. You can have there is a quick look at the distribution was here in in this plot. So this is the nominal redshift of the source if I take the central value of the distance and convert using Planck. So it's a bit cheating, but to have an idea. So you see the most interesting dark sirens to match with galaxy catalogs are this tail at low redshift. So let's say below redshift 0.1, 0.2, because that is also where typically we measure the distance better, with the notable exception I said.
Okay, and just a very naive question. I mean, in Euclid, people are all the time combining different cosmological probes to get a better constraint. And so can you do something like that with gravitational waves where you do the analysis conjointly with some other measurement?
We can, well, so the methods I described are already sort of a combination of different sources of information from mass and redshift. I think it is of interest to combine. For collaboration papers, we try to rely mostly on well understood public data. But in general, there can be room for improvement. Did you have any particular other technique in mind? So here we do not have like Euclid, two different, so a spectrometer and two different. If you want, maybe one analogy you could make is black holes and neutron stars. And we do that. So another improvement with respect to previous measurements was exactly to consider these sources together. Rather than doing two analyses separately, this was also done in previous papers. So analyze, say, black holes and neutron stars, and then combine. Or, for example, another thing, I went a bit fast on it. We analyze the bright siren separately and then combine with the dark sirens. So these things probably can be considered as an analogy of, say, combining the 3 times 2 point Euclid analysis. So we do it. The difference here is really that was really made in this point. So if you look closer what we are doing at the statistical level, I think the correct way is really to do one global thing. And the key point is that you need to, so the detector bias is one for all the sources we observe. So I think the perspective here in case we hopefully detect more coincidence events with bright sirens, it will be also incorporate all this information, including the selection model for the electromagnetic survey in this. So that would be my take for pushing forward in combining.
There's just one more naive question. Could you just explain again what you mean by the mass scale? Do you mean it's an uncertainty in the astrophysical model, is it?
It's not?
Is it an uncertainty in the astrophysical model?
Yes. So the mass scale, so do you want me to describe again the reason why this is informative,
like
or
words,
the model?
in 2 words.
Everything?
No, just in 2 words.
In 2 words what?
In 2 words, define again what you mean by the mass scale.
Okay, yes. By the mass scale, I mean the fact that in source frames, so for the intrinsic mass, black holes are more likely to form around certain masses than others. So this is the reconstructed probability that a black hole forms at a given scale, and you see a peak. So most of the black holes form around 10 solar masses.
Following this question, these features that on the observed mass distribution of the progenitors, black holes, notably the feature at 35 solar masses and this one. So is there any physical explanation, or you just observe them?
This is a subject of intense debate. So actually it's, in my opinion, the most interesting window that these observations opened is precisely the possibility of debating about this. So there are explanations, I must say. So it's not my field of expertise, so what I'm saying, take it with a grain of salt. I also must say, I don't think there is consensus, so I can tell you a bit. In particular, there is a lot of debate around this feature. So I think this one is accepted as a consequence of just mergers of black holes coming from a common system. So the 2 stars ending their life and entering a binary system around here. This bump is debated, and there is an interesting story around it in the sense that so something we do expect, and it's at least the modelers expect, so I believe them, is the fact that around 45 solar masses, if 2 black holes are just the remnant of the end of the life of a star, there is a phenomenon called the pairing stability supernova process, meaning basically the collapse is so intense for heavier masses that the remnant is disrupted. So there is no black hole formed through this channel if the progenitors are stars ending their life. So we would expect a gap here. So no black holes formed after this feature. Now, there are 2 problems. The first is predicting exactly where it is. So is it at 35 or at 42, 45? That depends on a number of assumptions in the modeling of the astrophysics, so there is some uncertainty. The second is, why do we observe things here? And the alternative is that these mergers could be the result of hierarchical ones, meaning 2 black holes, 2 stars end their life, they merge, and then this black hole merges with something else, and this evades the bound. So that there are papers now claiming the detection of this gap in the mass spectrum if you model the mass distribution with in a more complex way. They are on the archive, and so there is an intense debate around this, which I believe is very interesting.
Another question? Yeah.
Thank you very much for the talk. I don't know if observation of gravitational wave at different frequencies, for instance, nanohertz and the sort of kilohertz around this can help to improve the estimation of the H naught.
I definitely think so. They're in different ways. So different ways that depend on the specific band, because in different bands we observe different sources. For example, LISA is thought to potentially observe events counterparts from supermassive black hole binaries. So if you are able to detect the counterpart in coincidence and match with the LISA distance measurement, that will be an exceptional fact. And indeed, an interesting point that was raised recently is that if you look really at the correlations between, say, H naught and omega matters, so cosmological parameters, the LISA ones and ground-based one could have different correlation directions. So this might help breaking the generalities, say, between H naught and omega matter, or even in a more speculative way, maybe on the dark energy equation of state. So definitely, if you want me to speculate even more, since this is a discussion, the incredible thing will be even to detect a few events in the same event in different bands if these detectors operate on a suitable overlapping scale. So it is known that, and now the detection of these massive black holes, very massive systems by LIGO opens again the window to dreams of observing potentially same systems like this in LISA, and then a few months or years after in the ground-based detectors. In that case, the distance determination becomes very accurate because you can combine the data, which would be something exceptional. But in my opinion, it's still a bit in the realm of dreams for the moment.
Any other question?
Hello, thanks for the talk. Very interesting. At some slide, you mentioned that you fixed the matter density parameter to 0.3 something. And I was wondering, like here, you show that the redshift depends on the luminous distance and H0. I was wondering if relaxing the matter density parameter assumption changes the values on H0, and also if you also what dark energy density parameter you are fixing here, or if it doesn't matter at all. It might be a naive question, but yes, wanted to.
No, it's actually a very good question. So I skipped a bit on it. It's true. So we fix the matter density parameter for one reason, which is the computational cost of computing these galaxy catalog priors in each pixel in the sky prior to the analysis. What we do, though, is to try to marginalize over the background quantities, so both dark energy equation of state and matter density, when we switch off the galaxy catalog prior and just adopt a uniform prior. And what we observe is basically these two error bars compared to these. So they are basically unchanged. Which means, and if you look at the posterior distributions for omega matter and W naught, they are basically flat and recover the prior entirely. So shortly speaking, we are not sensitive to other changes on the background besides H0. The reason is that the sources are pretty close, and those which are a bit further away have such large error bars that basically they are not informative at this stage. So for the moment, we consider this assumption safe. Hopefully, it will not be at some point, which means we will be much more sensitive. But for the moment, it's okay. And this relates to the dark energy is the same. So I think the important thing about these tests of gravity I was mentioning is that, you know, here you might wonder if there is some degree of freedom or something that changes the friction here, right? This field or whatever should also enter the background expansion. And it usually does. It's the reason why we put it there in the first place, to explain the acceleration, right? So it will give a dark energy equation of state, which is not -1. So in principle, this effect is both here and in the background expansion. So in this dl, in the usual expression for the distance, there will be an evolving equation of state. Now, it turns out that this effect is orders of magnitude larger than the imprint of the equation of state. So this is the first thing to look at while looking at dark energy with gravitational waves. The effect on the equation of state at this moment is basically undetectable.
You told us about the feature in the mass distribution. Is there something that can be learned from the distribution of mass ratios, which also looked quite interesting?
Excellent question. So the answer is probably yes. Until a few months ago, not much, because the point is that the mass ratio is measured with much worse accuracy than the mass, the primary mass. So up to a few months ago, there was not much evidence of anything going on, so any feature or anything in the mass ratio. In this cosmology paper, we still took the most conservative assumption that there are no special features, but there are more dedicated studies that now point to the possibility that it's possible that black holes of 35 solar masses have a slightly different mass ratio distribution than the black holes at 10, so some additional substructure. It's not as robust, you know, not enough robust to include it in our cosmological models now, but we have these 150 more sources, so I don't exclude that this at some point will become interesting.
Right. Any other question? Seems not. So let's thank Michele again. And I remind you that this afternoon we have more talks about gravitational wave cosmology. And if you want to stick around with Michele, come to lunch with us and discuss more about this, feel free to come here and join us. Thank you all.